Hello everyone, welcome to Skill Dev. Trey here, and in this lesson, we are going to solve Pilot a Rocket. In this question, you work for RocketX, a company that's going to colonize Mars with the first humans. It's your job to write an algorithm to communicate with the ship flying to Mars from the base on Earth. It's important to communicate to the ship quickly, so you want to find the shortest path from Earth through the satellites to the ship. So to solve this question, you're going to write a function that takes in a graph as an adjacency list that contains the satellites, and this function returns an array of satellite IDs in the order from the Earth to the ship that follows the shortest path. The prompt states that the data for the graph is represented as an adjacency list. So let's see an example of what that means. An adjacency list is just a hash table to represent a graph. The keys of the hash table are the individual nodes, and the values are an array which show the items it's connected to. So it's the edges for an individual node. So here we see the base is connected to SAT0. SAT0 is connected to the base, SAT1, SAT3, and SAT4. SAT1 is connected to SAT0 and SAT2, as we see here, and so on. So it's simply a way to represent a graph by the nodes and the items it's connected to. The question doesn't give too much information or constraints about the adjacency list, so we're going to need to make some assumptions ourselves based on the context of the problem. The first question we need to answer is the graph directed or undirected? If it's undirected, that means communication can happen freely between nodes in either direction. If an edge exists, it means it exists both ways. A directed graph means communication can only happen in one direction, so it would need to explicitly tell us which direction the satellites can communicate. It's fair to assume satellites can communicate back and forth, so we'll assume it's undirected. The next question we need to answer is our graph weighted or unweighted? If it was weighted, that would mean certain paths would be more preferable based on some other factor, and this factor could be something like distance or speed of communication, but we aren't given any of that information. It seems that all paths are created equally, so we just want to know the absolute shortest, with no additional factors that come into play. So we'll assume our graph is unweighted. So we have an undirected, unweighted graph. Now let's think of the best way to traverse this graph. We want to find the shortest path. Anytime we see the phrase shortest path for a graph question, this almost always indicates breadth first search. So let's really highlight that and make sure that's clear. Shortest path is almost always an indication for breadth first search. The reason we use breadth first search for shortest path is because breadth first search checks its closest neighbors before going deeper into the graph. Since you're always checking the closest item, you'll reach a destination node by going through the fewest number of nodes. So let's just quickly visualize that to understand what it means. So here we have a breadth first search. We can see starting at 0, it checks the closest nodes first. Then we check each of those nodes' neighbors first before going deeper. This is how we can find the shortest path between any node. And these numbers here indicate the shortest number of nodes that we must pass through to get to it from our source of 0. So to implement breadth first search, we use a queue. When you visit a node, you add its neighbors to the back of the queue. Then you iterate through each item in the queue and repeat this process. Once you visit a node, you need to mark that you've seen this node already, so it's not added to the queue again. So now, let's walk through the graph using breadth first search. We start at the base, so this is the first node. Then we add its neighbors to the queue. This is simply SAT0. Then we dequeue this, and now we add SAT0's neighbors to the queue. This is SAT1, SAT3, and SAT4, or we see here 1, 3, 4. Then we dequeue SAT1, and we add its neighbors. Well, we've already visited sat0, so we need to make sure that's marked as visited so we don't add it again. The only unvisited neighbor from sat1 is sat2, so we enqueue that to the back. And then we dequeue sat3. All of its neighbors have already been added to the queue, so at this point we add no additional items. Then we dequeue sat4. We saw when we enqueued sat4, it was from sat0. 2 other nodes are connected to sat4, and that's sat2 and sat3. But since sat0 has already enqueued it, these paths that go through 2 and 3 will no longer be valid because they can't add it again because we marked it as visited. So to get to 4, it went base 0, 4. So at satellite 4, we then enqueue its neighbors. The only one we haven't visited is sat5. We enqueue that. We dequeue sat2. We've already visited all of sat2's neighbors. And most importantly, we've already visited 4, which is on our shortest path, so we wouldn't indicate we're going to sat4 through sat2. We saw we went to sat4 through sat0. So now we continue on. We have sat5. Its only unvisited neighbor is the ship. So now we've reached our destination. So we've seen that breadth-first search adds nodes to the queue through the shortest path, but we haven't seen how we can actually track this path and utilize it in the question. So let's think through that now. It's possible to reach any node through multiple paths. For example, we can reach 4 by going through 0, 3, or 2. But since we mark items as visited, we won't go through satellite 4 multiple times. We will only add it once when we go through satellite 0 and add its neighbors. So marking items as visited really serves 2 purposes. It makes sure we don't get in infinite cycles. So for example here, we could be in a cycle by going 0, 1, 2, 3, 0, 1, 2, 3 over and over. But since we mark that we've used a node already, we won't do that. We only go through each node once. But also, it has an additional benefit. Since we only go through a node once, it means we only go through that node from the shortest path when we use breadth-first search. So with breadth-first search, we find the shortest path to any node. For example, we could get to 4 through base 0, 1, 2, 3, 4, but we don't. With breadth-first search, we go through base 0, 4. But this is true of any node. We could get to 2 through base 0, 1, 2, or base 0, 3, 4, 2, but breadth-first search ensures that we don't do this. So if it's the shortest path to any node, when we add one additional node, it's just the next item in the path. Or to get to that next additional node, the shortest path just leads through the prior item. So the way to find the shortest path is to just find the node that leads to each next item in the list. So if we track that base led to 0, and then 0 led to 4, 4 led to 5, and 5 led to ship, that's just the shortest path. We need to track which item adds its neighbors to the queue, because the first time that neighbor is added is going through the shortest path. Because it's marked as visited, it will be added once and never again. So let's quickly walk through our shortest path from base to ship. It's base, satellite 0, 4, 5, ship. And we said we want to track the item that added this to the queue, because to get to any item, the prior item before it was the shortest path to get there, and then the shortest path to get to that next item is just coming from that previous item. So let's see the previous item for each of these nodes. Base is our starting node, so we're just going to set that to null. Then to get to satellite 0, we went through base. To get to satellite 4, we went through satellite 0. To get to satellite 5, we go through satellite 4. And then to get to the ship, we go through satellite 5. So we've mapped out the shortest path just by tracking it one node at a time. So looking at this, is there a good data structure we can use to map any node to the item that led us to that node? let's make it a little easier to visualize. It's starting to look like a data structure we've already seen. And that's a hash table. The keys are going to be the individual nodes, and then the values are going to be the node that led us to that item. If we track the previous node to any node in the list, that will indicate the shortest path. This can also be used to track when we visit a node. If it exists in this hash table, if we encounter it again, we'll see a node already led us through this path, so we won't check that item again. So it tracks the shortest path and also just the fact that we visited that node. So we can track our path as we walk, but how do we actually reconstruct it once we find the ship? How do we know the actual items that got us there? In this case, we only know the previous node. So we can't walk from the beginning, but instead, we can walk backwards. So if we know the item that got us to the ship, we know the previous node that got us there because that's how we're tracking the shortest path. So we go from ship to satellite 5, from satellite 5 to satellite 4, 4 to 0, and then 0 to base. And then we know we're done because base is pointing to null. So once we reach the ship, we can walk backwards to figure out the items that got us there. So the way we're walking backwards through the path is just by accessing the hash table for the keys. We call the hash table of the ship, which gives us sat5. We call hash table of sat5, which gives us sat4. Hash table of sat4 gives us sat0. Sat0 gives us base, and base gives us null. So we just keep accessing it for each item in the path. So then all we have to do, once we've walked backwards to find the shortest path, we can just reverse it, and that's our solution. So now let's just quickly highlight how we're solving this problem. We're iterating through the graph using breadth-first search. Then, anytime we encounter a new node, we add this node to a hash table, where the key is the node's value, and then the hash table's value for this item is just the node that was previous, or the one that was prior in the shortest path to getting there, because breadth-first search is the shortest path to any node. Then, once we reach the ship, every item in the hash table has the item prior to it in any given path. So then we just follow the ship's path backwards to the base, and this is the reversed order of the shortest path. Then we simply call reverse on that to get it in the correct direction. The big O complexity of this is v plus e time and v space. V is the number of vertices or nodes, and e is the number of edges. So we perform an operation for each vertex, and then when we try to add its edges. This is actually a very common time complexity for graph questions, so it's definitely something you should memorize. The space is simply O of v because in the worst case, we'll add all the nodes to our queue. And now, we're ready to write our solution function pilot rocket. We know we're going to be performing breadth-first search, so we'll also use this queue helper class that we're given. And really, this solution boils down to two things. We need to implement breadth-first search, and then we're going to use a hash table to track the path that we follow to go from the first node to the ending node. We always have the same starting and ending node, so for better code, let's just define those in constants. We know we're performing breadth-first search, so let's just initialize a queue now to handle that. We always have the same starting node, so we'll enqueue that as well. We're tracking our path using a hash table. The key is the current node, and the value is going to be the previous node that led to this item. Then, once we reach the ship, we can walk back from the ship to the starting node at the base. We just follow each key to its value and retrace the path this way. And now, we're ready to start the breadth-first search. We continue to iterate through the graph as long as there are nodes in the queue. If our while loop breaks and we don't find the ship, and then the final condition is to return null, indicating there wasn't a path. Each iteration, we just remove the front item from the queue. Then we iterate through this node's neighbors and also add those to the queue. The input is an adjacency list, so we can just access its neighbors by calling it by the node's ID, which is the key. Now we need to check if we visited this node before. We're actually using the previous node in path hash table to indicate if we've reached this node yet. So if the previous node in path for the connected node or the current neighbor is undefined, that means it's not in the hash table. We haven't visited it, so we can add it to the queue, and then we can also set the current node as its previous node, because this is the first time that we're reaching this connected node. So we enqueue it, and then we set the node that we're at in the while loop as the previous node to this one that we're accessing. And the final thing we'll do is check if we reach the end node. And we'll actually do this before we try to add neighbors to the queue because we know the problem is over. We'll now write a function, getShortestPathToShip, that will reconstruct the path using the previous nodes in the path. So we initialize the function, and the return value of the function is going to be an array of the node IDs from the base to the ship. We know we have to walk through the hash table backwards because the only value that we actually know is in the path is the ship itself, so we walk to each previous node to reconstruct the shortest path. So we continue to iterate until we reach null, which means we've returned to the base. The only node that had a previous value of null is the base because nothing came before it. It was the starting node. So we just push each item to the path to ship array. And then we move to the previous node in the path by accessing it through the hash table. So the keys are the current node and the values are the previous node. So we can continue to step backwards by going to each value for the current key. And now our path is complete, but it started at the ship and went to the base. So we just reverse it to get it in the correct order. So in this question, we implemented breadth first search from scratch, and then we also track the path using a hash table. Thanks everyone, and I'll see you in the next lesson.